Okay, guys, today's topic is 9.5, which is the Doppler effect, which is going to be a phenomenon that happens to waves when either the source or the observer is moving. If you look at the essential idea of this topic, the Doppler effect describes the phenomena of the wavelength and or frequency shift when relative motion occurs, relative motion being the motion between the source of the waves and the receiver or the observer of the waves. Basically, you'll need to understand the Doppler effect for both sound waves and light waves. What you should be able to do, your applications and skills, you should be able to sketch and interpret the Doppler effect. So that's understanding the diagrams of how it works. You should be able to describe situations where the Doppler effect can be utilized. And of course, you should be able to solve problems. That's where the equations are going to come into play. Okay. Let's see. And some of the guidance here when we're dealing with electromagnetic waves, the approximate equation should be used. This is the approximate equation down here, the third one. And situations to be discussed. We should talk about the Doppler effect in radars and medical physics, and also its significance for the redshift and light spectra of galaxies. Notice that there's three equations that we'll be using. One of them if the source is moving, one of them if the observer is moving, and the third one is used. It's an approximate equation that works really well when we're talking about the Doppler effect with light, or electromagnetic waves. So just first things first, we got to get a feel for what the Doppler effect is. And basically, it is a change in the observed frequency of a wave due to either the source of the wave moving or the observer or receiver of the wave moving, or both. As long as there's relative motion between the source and the observer, there will be an observed shift in frequency. Sometimes there will also be an observed shift in wavelength. So kind of the classic example of the Doppler effect is like a siren. If you have like a police car going at real high speeds coming toward you on the highway, you're standing next to the road. As the siren's approaching, it's going to have a higher pitch. And as it's receding, as the car is driving away from you, the pitch is going to be lower. Now you got to make sure that what we're talking about here is the pitch. That's what you experience due to the frequency of the waves. Don't concentrate on the volume. Obviously, as a car approaches and leaves, the volume is going to get louder and softer because the car is getting closer and farther away. And that's not the effect we're talking about. What we're talking about is an actual change in pitch or in tone. And the wave property that most often changes that we're going to talk about is the frequency. Occasionally, depending on the situation, you'll also get a difference in wavelength as well, but the frequency of the waves will always change if there's relative motion between the source and the observer. So another classic example of the Doppler effect happens with car races. And one of the reasons we talk about Indy cars and NASCAR cars, you can hear the Doppler effect more, it's more pronounced because the cars are traveling so fast. So I'm going to show you this little video clip. And what I want you to listen to is not how the volume changes. The cars are going to get louder when they get closer, and they're going to get quieter when they get farther away. But I want you to hear how the pitch of the engine changes, how it's like going meow when they go by. And then in this video, you're also going to see from the perspective of being in the car, the driver of the car who's moving with the source of the sound doesn't hear any shift in pitch whatsoever. So let's play the video and see if you can hear all those things.
Back in the field. Actually back.
All right, so I hope you could hear that. As the cars go by, they're going meow, meow. So the tone of the engine sound is changing. It has a higher pitch when it approaches, a lower pitch when it recedes. But when you're in the cockpit of the car driving, the pitch stays constant because you're moving along with the waves. That is a classic example of the Doppler effect. Now here's a visual representation of it. Here's a fire engine rather than an Indy or Formula One race car. Here's a fire engine. Its siren is going. Notice that when the fire engine is at rest in picture A here, the waves going forward and going backward all have the same wavelength, have the same frequency. So the woman in the pink hears the same frequency as the gentleman in the yellow. But notice here, picture B, the fire truck is now moving. The fire truck is driving to the right, from left to right. That's the velocity of the truck, the source of the sound waves. And just by virtue of the fact that the truck is moving, the wavelengths of the waves in front of the truck get compressed. And therefore, the lady in pink is going to hear a wave with a higher frequency, since it has a smaller wavelength. Because The speed of the wave is going to be the same in all of these cases. Remember, the speed of a wave is determined by the medium through which it travels. Since the medium is just the still air here, the wave is always traveling at the same speed. If you remember this equation, it's kind of a classic one, velocity of a wave equals wavelength times frequency. If the wavelength for the lady in pink is diminishing, then the frequency has to be increasing in order for velocity to stay constant. The same will be true for the gentleman in the yellow. Since the truck is receding from him, these waves get stretched out. You can imagine their wavelengths are longer. And since the wavelength is larger, the frequency is smaller, and it is a lower pitch. The woman and the man will observe different sounds just by virtue of the fact that the fire truck is either approaching or receding. Here's another image of it where the waves are drawn in their circular form rather than just little pieces of them. Notice on the left, there's the car is standing still. The waves are the same in all directions. Therefore, the sound is the same in all directions. The image on the right, the car is driving to the right. The waves get bunched up in the direction of motion. The wavelength is smaller. The frequency is higher. And the opposite is true where the car is driving away. So this is the diagram that I'd be expected to be able to kind of understand, be able to maybe even draw this or somehow explain why the Doppler effect is occurring when the source of the waves is moving. So this is all what it looks like when the source is moving. It's a similar effect when the receiver is moving and the source is stationary. You still get a Doppler effect where the frequency, the observed frequency, will shift, but it's for different reasons. So I want to show you this little video that I think does a good job of showing you what's going on when the source is stationary and the observer is the one that's moving. So let's take a look at that. Notice that the waves coming out from the source, their wavelengths are staying constant. So the difference here now is that the wavelength of the wave doesn't change. The wavelength stays the same in all directions, but because the observer is moving through the waves, the apparent motion or apparent speed of the waves has changed. And if the apparent speed has changed, then the frequency will also change. And so let's just look at that one more time, and so you can observe what's going on there with that. Oh, shoot. Bear with me here one second. Okay, notice that, again, the wavelength is staying constant, but because the observer is moving through the waves, the speed of the waves appears to change. Okay, the speed is increased when the observer is moving towards the source, and the speed is decreased when the observer is moving away from the source. Okay, just to help you get the conceptual component of this concept, I'm going to show you another little website here that it does a good job of explaining the Doppler effect. So here's the sound. Notice the tone changes when the car passes. It's not the volume, but it's the pitch we're talking about. And so what this shows you is there's sound waves from a tuning fork to the ear. This, I think, is a real good representation. The red ball is the source. Notice the frequency of that red ball as it oscillates, creating some sort of a wave. In this case, we'll call it a sound wave. The blue ball is the receiver, and notice that it's oscillating not necessarily perfectly in phase, but it is oscillating with the same frequency because there is no relative motion between the source and the observer. If the observer moves towards the source, notice that it's moving through the waves more rapidly, and see how the blue ball is now oscillating at a higher frequency due to its motion towards the source. If the blue sphere is moving away from the source, notice that it oscillates more slowly at a lower frequency than does the red one, which is the source of the waves. And you can even imagine if the blue sphere were moving away at the speed of the waves, it wouldn't oscillate at all. Okay, that's kind of the extreme example. So definitely different frequencies. Now notice the source is moving. If the source is moving away from the receiver, then the frequency that will be received will be lower. Notice the blue sphere is oscillating more slowly than the red sphere, the source that's creating the waves. All right, and then we'll get into the equations and things like that. Okay, so those were the concepts and the diagrams that you have to understand. Now we're going to get into the math of it, the equations. And first thing, before we look at the equations, I want you to understand that you need to conceptually understand whether the frequency of the wave should be increasing or decreasing. If the source of the waves and the observer are moving towards one another, the frequency should be going up. If the source and the observer are moving away from one another, the frequency should be going down. And we have two sets of equations depending on what is moving, the source of the observer. So the first one is when the source is moving. And this is what the equation looks like. It roughly looks like this in your data booklet. And what you need to recognize is F stands for frequency. So F prime, what you're solving for here is what the new frequency or the observed frequency will be. You use F, the original frequency, that's the frequency from the source if nothing is moving. V in this equation is the speed of the wave through the medium. And U is how fast the source is moving. Now notice you have an option here. In the denominator, you have an option of either doing V plus U or V minus U. Now you can go and memorize which one is when the source is moving towards the observer and which one is when the source is moving away from the observer, but I choose not to do that because I find if I can't remember it, I don't remember it. What I choose to do is say, hey, if the source is moving towards the observer, I know that F prime better be larger than F. And when I do my math, if F prime is smaller than math, then I did the wrong thing here, and I have to do the other one. Or if you're really quick, you can say, oh, well, if it needs to get bigger, since this is in the denominator, this needs to get smaller, so I'm going to use minus. But I'm not always that good either, so I always just check my work. If the source is moving towards the observer, I expect this number, F prime, to be larger than this number. Okay? That's the way I like to think about it. So you can choose a different way if you want to, but I find that that works pretty well. And then, of course, this next equation we have is if the observer is moving rather than the source. They look very, very similar. Just now the addition subtraction part is in the numerator rather than the denominator. Again, you still have a plus or minus, and that's because you're going to do one if the observer is moving towards the source and one if the observer is moving away from the source. Again, if the observer is moving towards the source, you expect F prime to be larger than F if the observer is moving towards the source. And in order to get a larger number, that's going to be addition here. I can do that in my head. But again, just always think through your answer and make sure that when you're solving a Doppler effect problem, that the frequency did what it was supposed to do, whether that is to get larger or to get smaller. And again, a thing that I want you to recognize here is that these equations deal with the frequency. The frequency, the observed frequency, will be what always changes. And that can be either due to a change in wavelength. Again, the wavelength will be different if the source is moving, or to an altered wave speed. And the wave speed will be different if the observer is moving. That's the wave speed relative to the observer. You can combine these Doppler equations with the classic wave equation, wavelength times frequency. Just remember that, because that will help you solve some situations as needed. Okay, so here's a pretty basic practice problem. This is not an IB practice problem. This is just practicing using the equations. So go ahead and hit pause. Try this out. It's asking you to find the frequency, the observed frequency, as the car is moving towards you, and then again as the car is moving away from you. You can use the speed of sound in air as 343 meters per second. Hit pause. Solve this, see what you get. All right, hopefully you pause this. I'm going to show you the answers now. I'm not going to walk through solving this one because this is basically just plugging it into the equation and trying to get the right answers. But as it was moving towards you, you should have gotten a higher frequency of 1726. As it's moving away, you should have gotten a lower frequency of 1491. So what are some of the uses of this effect, the Doppler effect? What sort of applications? It turns out there's quite a few. If you've ever gotten a speeding ticket by a police or a sheriff using a radar gun, it's the Doppler effect. Basically, they have a gun that shoots out radio waves of a certain known frequency. When it hits your car, if your car is moving, that's a moving observer, you're going to observe those waves at a different frequency. Those waves will reflect off of your car and go back to the radar gun, which then they're received at a different frequency than they were sent. The little radar gun's got a little computer in there, figures it all out, and by doing the math, they can figure out how fast you're going just by the Doppler shift of the frequency of the radar waves that are sent. Pretty cool technology, even though it's frustrating when it works. Now, this is kind of crazy. In medicine, they can actually measure your blood flow using ultrasound and the Doppler effect with ultrasound. Ultrasound are waves, sound waves that are higher frequency than we can hear. They can, shoot those sound waves into your body, and the sound waves will bounce off of your moving blood cells as the blood is flowing through your veins and arteries. Those sound waves bounce off of your moving blood cells. That shifts their frequencies, and then you can measure that altered frequency and get a measurement of how fast your blood is flowing. Crazy, crazy. You might have heard of Doppler radar. Radar has been a really powerful tool, one, for military, but also, two, for meteorological purposes, for the weather. And Doppler radar is even better because what they can do is they can shoot radio waves into these clouds, which they bounce off of the particles in the cloud, and then when they're received, there will be a Doppler shift of their frequency, which can give you an indication of the motion inside of the cloud. That can help measure precipitation inside of a cloud. It can also help measure rotation and the development of things like tornadoes. And so it's just a more powerful tool that meteorologists use. And the field of astronomy has found many, many, many uses for the Doppler effect. Much of what we do in astronomy is derived from the light we observe. Since we can't go to distant stars, we can't go to distant galaxies, all we can do is observe the electromagnetic radiation coming to us from these objects, and we can glean all sorts of information from those electromagnetic waves, and the Doppler effect assists with that. For example, binary star systems. A lot of the stars we see appear to be singular stars, but when we look at the light of that singular star, we can sometimes see Doppler shifts of the spectral lines indicating that there's more than one star there, and it turns out that's true in more than half of the cases of the stars that we see. Rotating galaxies. Okay, this is something that's kind of crazy. When you go to a science fiction movie and the guy's sitting on the spaceship looking out at a galaxy that's sitting there spinning while you watch, that is so ridiculous. Because it takes the Milky Way, for example, it takes, what is it? We go around every 100 or 200 million years it takes us to orbit once. You're not going to observe that. So how do we know these galaxies are rotating? They appear to be stationary. Well, the way we know they're rotating is by observing the Doppler shift of the light coming from either edge of the galaxy. We use that to measure the rotation of stars as well. And then the big one, this is kind of crazy, but one of the biggest discoveries in astronomy is that the universe is expanding. And it was figured out mainly because of a Doppler shift of the light of distant galaxies. That every galaxy we looked at, the light was stretched, was longer, and so though it's technically not the Doppler effect, it's a very similar phenomenon that helped Edwin Hubble discover that the universe is expanding about 100 years ago when he discovered that. So let's talk about the Doppler effect and the equation when we are talking about light. Since light moves so much faster, we can actually simplify the equation quite a bit, and you'll end up looking at something kind of like this. When you observe light, the change in frequency of the light divided by the frequency if it were stationary, okay, that ratio is equal to the same ratio for wavelengths, which is approximately equal to the speed of either the relative motion of the source and the observer divided by the speed of light. And the reason this equation works out, it really only works out if the speed, the relative motion between the source and the observer is way, 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 way smaller than the speed of light. C is the speed of light. And that's almost always the case when we're talking about electromagnetic radiation. Rarely do we have observers or sources that are moving near the speed of light. And when we're talking about light, again, we're talking about a shift in frequency. And frequency, the differences in frequency of light in terms of visible light is how we see different colors. So red, orange, yellow, green, blue, indigo, violet, those all have different frequencies. And it turns out red is a lower frequency and blue is a higher frequency. And so when things are moving apart in astronomy, when things are moving away from one another and the light is stretched out, we say that it has been redshifted. And again, so Edwin Hubble, when he was making his discoveries back in the early 1900s, one of the things he discovered was every galaxy he looked at had a redshift to it. The light was stretched, and that led him to the assumption that the universe is growing. It's not stationary. If things happen to be moving towards one another, then we would say the light is blue shifted. And that's a more rare phenomenon, but it does happen. The Andromeda galaxy, for example, is moving towards us. It's one of our biggest neighbor galaxies. It's moving towards us. Its light is actually blue shifted. And yes, we will collide with it in billions of years down the road. Okay, here's another practice problem, this time using the Doppler equation for light. I want you to hit pause and give it a try, see what you can find out. In this case, you're calculating how fast the galaxy is moving. All right, I'll show you the answer. I'm not going to walk through this one again because it's kind of just using the equations, but hopefully you were able to get this number. It's not a negative. I mean, I guess it could be a negative since it's receding, but 6.34 million meters per second, which is, just to give you a feel for that, it's 2% the speed of light. Okay, 2% the speed of light. Now here's an actual IB multiple choice question about the Doppler effect. Go ahead and pause. Take a look at this, see what you can do. All right, hopefully you're recognizing that the frequency is not gradually increasing, or it's definitely not increasing as it recedes. It's not a gradual thing, it's a very quick change, and the frequency will be constant as it's approaching and receding at a constant speed. So D is the correct answer for this one. Okay, here's another IB multiple choice question about the Doppler effect. Hit pause, try it out, see what you get. Okay, so this one's got a couple different things to it. Notice that the observer is stationary, right? And the source is moving. So we talked about that a little bit. When the observer is stationary, the speed of the wave is the same for the observer and the source. The wave speed changes when the observer is appearing to move through the waves, because that's a relative thing. It's like you've changed the medium from still air to moving air. And so, since the source is the thing that's moving here and it's moving away, that means the wavelengths will be changed. And if the source is moving away, you can expect the wavelengths to be larger, which leads us to B or D. And then since the speed is not changing because the observer is stationary, then we're going to go with answer B. Okay, so let's review a little bit of the syllabus here and see how we did. You need to kind of understand what the Doppler effect is. You should be able to sketch and interpret those drawings. You should be able to describe situations where the Doppler effect is used. And finally, you should be able to solve problems involving the change in frequency or wavelength observed due to the Doppler effect to determine the velocity of the source observer. Now notice this says to change in frequency or wavelength. Notice the equations we have only deal with frequency. So that's when you're going, if they ask you something about wavelength, that's when you're going to have to throw in the velocity equals wavelength times frequency equation for waves. Okay, that's not in your data booklet under this section, but it is in the previous section for waves. Remember about the approximate equation for light, that's this equation here. And finally, the situations where the Doppler effect should be discussed include the effects in radars and in medical physics. I believe we talked about both of those, and its significance for the redshift in the light spectra of receding galaxies. All right, hope you